Hello, everyone. The very first link I sent you, and someone said that it didn't work. Actually, what happens is it was the correct URL, but what happens is that sometimes when I cut and paste into the Juval email system, it makes a mess of it, and it doesn't properly do the highlighting. So if you just click, it's just like regular text. I sent it a second time, but hopefully everyone's here. And as usual, I don't think I made the classic blunder of keeping myself muted. I can see my levels bobbing up and down, but always let me know if if you see my mouth moving and you don't hear anything. Let me know in the chat so that I don't make a fool out of myself just talking away. This week, you should have watched two videos, and they're both on 2D kinematics. And one of them was 2D kinematics, assuming constant acceleration, and that's basically falling. Okay. Now we did do falling before, but we did it with 1D, so we were restricted to just things going up and down. Okay, so you throw something up and it comes down, or you could throw something down and it just speeds up as it goes down, and so on. Or even like constant acceleration. Say you're driving your car along a road and you step on the gas, you speed up. That's acceleration. Or you're driving at a constant speed, you hit the brakes and you slow down. That's also acceleration. It's actually we call it deceleration, but it's acceleration in the opposite direction to the velocity. So, but you were stuck on a straight line in 2D. You're in a plane, and so now we can talk about throwing things up and down into the air, and that making that characteristic parabolic arch as something goes up and down. Okay, and 2D is really enough for us. You could do 3D as well, but usually when you throw things, it's called projectile motion. It's usually within a plane. I mean, it is 2D, but within it is a parabola, but it's within a plane. Could do 3D, but 3D adds extra complications. You don't get as much out of it, so 2D is enough. And then the other type of motion that you should have looked at was going around in a circle. Okay, and that's uniform circular motion. Later in the course, we're going to do more generalized rotational motion, but uniform circular motion means you're on a circle, so hence the name circular, and uniform means you don't speed up or slow down. You're always going around a circle at the same speed. Okay, later on we're going to allow for like some more crazy possibilities, like, yeah, you're going in a circle but you go slow and then you speed up, or you're turning fast and then you slow down, and that's generalized rotational motion. Right now we're just on a circle and just going at a constant speed. Okay, and so I've got two problems for that, and I'm going to leave you with a couple of practice problems which are a variation on the problems that I gave you. And then of course over the weekend I will give you the assignment, and the assignment will have a couple of questions, which of course you should try early and then ask me questions during the week. Don't wait till don't wait. Well, we have the test next week, so you probably want to do it early anyhow to get it out of your way. I'll make it due on Friday as usual, but get it out of the way early as part of your studying, and then you can always ask questions about it. And those are the practice problems that you're doing leading up to the test. On the test, I won't give you any surprises. I mean, like if you've done the questions that I've given you, you've watched all the lectures, you've done all the questions that I've given you, you should be fine for the test. Okay, let me take a look if there's any questions in the chat here. 13 people listening, and no one's asking any questions. Let's just start. Okay. So here's my first question. My first question is actually kind of I wouldn't say it was a hypothetical. I kind of set up a sketch of a problem at the end of my lecture on constant acceleration, 2D constant acceleration, and it was basically where I was at the bottom of a hill throwing a rock, and it was landing on top of the hill. The problems that I did in greater detail were in the pre-recorded lecture was, I was on the top of a hill and I threw it and it landed on the bottom. So we're going to do the opposite of that. And here it is. I'm standing at ground level. Okay. And I toss a ball with a velocity of 25 meters per second, which isn't that fast. Okay. Easy to do at an angle of 60 degrees above the horizon. And I'll describe what that language 60 degrees above the horizon means. Okay. And it lands at the top of a hill, which is 20 meters high. Okay. So the first part of this is the situation. All right. And we'll sketch that in just a second. And I've got 5 questions. Okay. First is how long until it reaches maximum height. Obviously this ball is going to go up. It's going to reach a maximum height and come down. Okay. And what is the maximum height that you, so how long until it reaches maximum height? What is that maximum height? That's part B. Okay, so part A and part B are really part of the same uh, question, or same set of procedures. And then I want to know how long before it lands on the top of the hill. Okay, and that's obviously got to be longer than when it reaches maximum height, because it's going to take so long until it reaches maximum height. And then it's going to travel a bit further until it lands on the top of a hill, because it lands on the hill on the way down. Okay, and how far did it travel horizontally before landing on the top of the hill? And what was the velocity just before it reached the top of the hill? Now, velocity is a direction. So in Cartesian, it would have an x and y. In polar, it would have a magnitude and a direction. I just want the magnitude here. Okay, I could ask for the direction too, but I'll just do the magnitude, and that's good enough. Okay. For practice, what I'm going to ask you guys to do later, and you could do this on your own, and then as usual, ask me if you don't know how to do them. Repeat the entire problem. Okay, but assume that there's no hill and the ball just lands at ground level. Okay, so you know, it's the parts A and B are going to be the same, because it'll still achieve the same maximum height. Okay, but you know, go through it again. Even if you get the same answer, it's worth going through it, going through the steps. Okay, and then but this time it's not going to land at the top of a hill. It's actually going to come down to ground level. Okay, so repeat all of those questions and things will change. Okay, and then repeat it again, but this time do kind of like what I did in the pre-recorded lecture. This time you're on the top of the hill, which is 20 meters high, and the ball lands at ground level. Okay, and then even the maximum height will change. There'll be a lot of things that change there. Okay, so those are two variations on the question. But if you think about it, you've kind of gone through all the possibilities here, where you know you're lower than where the ball lands, you're at the same level as where the ball lands, or you're at higher level than where the ball lands. Okay, and this corresponds to three possibilities of the parabola, how you're going to clip the parabola, whether it's purely symmetrical, and that's actually where it lands at ground level, or whether it's clipped earlier or clipped later, and that's whether you're on the ball lands on the top of a hill or below where it's been thrown. Okay, and so these three problems together make a very good unit to look at. Okay, there are still more variations on them, but they could get really hard. Like for instance, I could tell you where it lands and ask you to calculate the angle, and that requires some fairly, well, I wouldn't say hard trigonometry, but there's some trig in there, and it's a little bit harder than I think you want to do. I mean, basically you wind up getting tangents, and you get a quadratic with sines, cosines, and tangents, and that's kind of ugly to work with, but it could still be solved. Okay, we won't do those. Okay, and then question number 4 here we'll do together, and that's just an example of uniform circular motion. Okay, so let's start here. And just to remind you how you proceed in solving these problems. I mean, the questions are multiple choice, so on the test, and they're just like the assignment. They'll look the same, okay? But you know, like you know, just because they're multiple choice doesn't mean you can avoid going through the steps, because you'll make a mistake if you don't. Okay, and it's very easy to make mistakes in these and get lost. So the steps are draw the diagram, and then even in drawing the diagram, there's usually 3 levels to doing that. The first thing is just draw the picture of what you're seeing, and then draw a coordinate system. And in this case, because it's 2D, that's going to be x and y, and then try to identify initial position, final position, initial velocity, final velocity, acceleration, and time. And this time, when you say initial position, it's both the x and y component. Okay, so there's 2 things going on there. All right, looking in the chat for any questions. People look okay. Don't be afraid to stop me. The whole point of the live streams is, you know, if you've got any questions. All right, let me switch to my drawing board here. Okay, oh, I guess I've got my diagram from earlier. That's okay. We'll just start off with a new one here. Let's create a new one here and zoom in a bit so that it's a little larger. Okay, so you can't see the question right now, but let me just reread it to you. The question is, I'm standing at ground level and I toss a ball with a velocity of 25 meters per second, 60 degrees above the horizon, and it lands on the top of a hill 20 meters high. Okay, so draw the ground level and the hill and then the trajectory of the ball. Okay, and I'll do that in black here. So here is ground level like that, and then there's a hill here like that, and then here's the top of the hill like that. And I know that it's, 20 meters high, but I won't draw that in quite yet, okay, just to try to avoid making too much of a mess in the diagram. And I'm not going to do my stick figure. Here I am here, that little dot there is me, and I'm going to throw it at 60 degrees. 45 degrees is kind of like, whoops, that's not even 45 degrees. 45 degrees is like that. 60 degrees is a little higher. It's, hold on. It's like this, and it'll go up, 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 and it comes down like that, and it lands at the top of the hill like that. Okay, so there's your first step. Okay, basically I've just drawn the hill, I've drawn, you know, the trajectory of the ball, and so on, and nothing more. All right. And the next thing is you want to put a coordinate system, and you are free to put the origin where you want. But I'm going to, on the test, I will definitely tell you where to put the origin. The reason I'm going to do that is because I'm going to, like, you'll see in the assignment that you get next week. I'm going to slightly walk you through the problem, and so I'm going to say what is the initial position, x and y coordinates, x and y components of the initial position. If you choose your origin differently than me, your x and y values will be different than my x and y values. And so, and since, you know, I want you to, you know, choose the right answer, I better make sure that you get the exact same numbers I do. And to do that, you know, we have to choose the origin the same. But, you know, since we're doing this problem from scratch, we could choose the origin anywhere we like. I think it's pretty obvious that the easiest thing to do is to choose the origin where at the initial point, like where the ball is, like right here. Okay, so we're going to choose the origin right there. All right, and in order for the equations to work the way I wrote them, and you'll see them again, there's equations in y and there's equations in x. In order to get them to work, you're going to have to choose the x-axis horizontally like this. Okay, so that blue line right there, that is the plus x-axis. All right, and I'll explain why you have to make this choice when I show you the equations. So the x-axis, for the equations to work, the x-axis has to be purely horizontal. The y-axis has to be purely vertical, like that. Okay, so there's the plus y-axis, like that. And the origin is where they meet. And so it's pretty obvious that the origin is down here. I'm just going to put a 0 there like that. Technically, I guess it should be 2 zeros, 0, 0, because it's 0 in the x and 0 in the y. But I'll just put 1, 0 right there. That's the origin. And we also need to put a temporal origin. That is, like, where is it at t equals 0? Okay, or at what point on the trajectory on this black line here? Where along that black line is t equals 0? And I think obviously when I release the ball, that's a good place to call t equals 0. So this point down here, it's not only the origin in space, it is also the origin in time. I hope that doesn't confuse you. I mean, you kind of like have to say, like, you might have two rulers there, but you also have to say at what point in this trajectory do I actually press the stopwatch and start 0? And that 0 looks terrible. That's a little bit better, okay? You know, and I'm going to say as soon as I release the ball, that's going to be my 0, okay? So I did that fairly carefully, but I mean, explaining it in detail. But I mean, I think this is pretty obvious, okay? So you just draw your x-axis horizontally, your y-axis vertically, and where the two cross, that's your origin. Choose it where I tell you on the test. If this were like you were doing this without any kind of constraints, you could choose that origin anywhere, and also say where is the thing at t equals 0. All right, and there you go. All right. Now the next thing is, and I'll do this in red, and I might run out of room here, but it's asked the question, what's the initial position, what's the final position, what's the initial velocity, what's the final velocity. Okay, so the initial position is actually two numbers. Okay, so position is like where is it. But if you ask the question, where is it? Now, I'm just going to put a random dot here. I'll get rid of it in a second, okay? If I say, where is that dot? All right. You know, just giving me an x value is not good enough because that just measures along. That would be just like measuring along the x ruler here, the x coordinate. And then you go, oh, it's, you know, it's like somewhere where my cursor is there, like that. You know, it's like there. And but that doesn't tell you how high it is. That just tells you how far vertically you have to travel to get underneath it, but not how high it is. You could say how high it is, but that doesn't tell you where it is either because it doesn't tell you how far vertically it is. So all of these things like initial position, final position, and so on, they always have to be pairs of numbers. Okay, let me get rid of that dot. And so the initial position is right here, obviously, like where the where t equals 0 is, and it's two numbers. It's x naught, which is the x component. Now I know in 1D we called x naught the initial position, but in 2D x naught is just the x component of the initial position, and then there is y naught. Okay, so those two together, I'll put a little bracket there like that. those two numbered together specify where in the xy plane the object is initially, okay? And this is Cartesian. Everything is done in Cartesian. The equations are in Cartesian, but sometimes, and you'll see this with the velocity, sometimes the information is polar, and so you're going to have to convert from polar to Cartesian. That's what's going to happen with the velocity. But let's do the initial position first. It's at the origin, so that's pretty obvious. X is 0, x naught is 0, and y naught is 0. Okay, so ask if you have any questions about what I just did there. Those two numbers together, the way I have them bracketed there, that is initial position. So on the test, one of the questions will be, what is the initial position? And you'll see I'll have x is equal to something, y is equal to something in all of my choices. And you go, well, why are there two numbers? Because it's a vector. Okay. So there it is. The final position is going to be here. All right, there's the final position. And it's now, we're going to call that just x and y. All right. And again, those two together, those two paired together, are the final position. Okay. And you say, well, what is x? Well, we don't know, because if you just were to run along here, under the along the blue line, and you say, well, what's the x? The x is it's the projection down here like that. So if you imagine like a shadow being projected straight down from where the object is to the x-axis, right to there, you say, well, what would I read off of that x ruler? And the answer is, you don't know. Okay, you can calculate it. That's part of the problem. But at this point in the game, you don't know, because if you read the problem, nowhere in the problem do I tell you. Okay, and so you just don't know. The y coordinate, and I'm not going to draw the y. Well, maybe I'll draw it a little, but if you did the projection, it'd be like over here. Let me get rid of that. I don't want to make it too messy. The y projection, it's at the top of the hill. And so that's going to be, oh, you know what, guys? I'm sorry. I apologize. That's for part C. For part A, it's how long does it take to reach maximum height, okay? So maximum height is right here. All right, so that isn't wrong. It's just that's for part C. For part B, the maximum height is right there, okay? So do you see where I made the extra large dot at the very top of the parabola? That's maximum height, but you're still in the same situation in terms of x, okay? So just to not make the diagram too messy, I'll draw it now, but I'll remove it. That would be your x. Your x would be all the way down to here. And again, you wouldn't know where that is, okay? So let me get rid of those dashed lines. So you don't know your x for maximum height. And you know what? You don't know your y either. You don't know that either. Because after all, that's what you're trying to calculate. When you say height in these equations, that's basically y. Okay? So you don't know the, for the final position, you don't know the x, how far along vertically it's traveled. You don't know how high it's traveled horizontally. Okay? Now, you say, well, I keep calling this final. All right, and that's what, like any textbook that you would see would call it final. But you say, but it doesn't end until it gets to the top of the hill. I know, but as far as we're concerned, question A, when it says how long until it reaches maximum height, what you mean by final is just like, that's the point at which you're interested in the motion, okay? And so, it happens at some time here, which we also don't know, all right? And so that's a question mark, all right? So we don't know a lot about that point. We don't know its distance that it traveled horizontally. We don't know the distance that it traveled vertically to get there. And we don't know the time. Okay? And so there we are so far. All right. So any questions with that up till now? And so I've got initial position there. I've got the final position. And now there's initial and final velocity. Here's what I'm going to get into a little bit of trouble. I'm going to run out of room here, so I'm going to probably have to switch over to the other thing in a second, to my other whiteboard in a second, the text editor. But for the initial velocity, there's actually two pieces to it. We have to do Cartesian, v naught x and v naught y. I'll write them right here because I don't have any other place to put them, okay? But if you read the problem, I don't give you v naught x and v naught y, all right? So I give you the following. With a velocity of 25 meters per second at 60 degrees above the horizon, what I'm telling you is basically how fast it's traveling this way. That is its magnitude, and that's 25 meters per second. Where can I write that? I can write that here, 25 meters per second. That's like just how fast I throw it without regard to the direction. And 60 degrees above the horizon, okay, the horizon is the x-axis. And so if you were to measure like this, counterclockwise from that x-axis along that red arrow there, you would measure an angle here of 60 degrees like that. Okay? And so you take a look and you say, well, I've given you what's called a magnitude. That's just like how fast it's going, irrespective of direction. And I've given you an angle measured counterclockwise from the positive x-axis. So what have I given you? I've given you polar information. But you don't want polar information, or you can't use the polar information directly. You got to convert it to Cartesian. Okay? And so for the initial velocity, you need v naught x and v naught y. And you go, well, how do I get that? Well, it's basically the magnitude, v naught, times the cosine for the x of the angle. This is the general formula. And for v naught y, it's v naught for the y component sine of the angle. What we've basically done, and let me use a different color here. We've basically done is we've taken the red vector there and we've broken it into two pieces. We've broken it into, I don't know if that works so well. Okay, we've broken it into an x component there. That's that green arrow that I'm trying to draw there in extra thick. And we've broken it into the y component there like that. Whoops. There we go. Yeah, I guess you can kind of see that. I mean, the view I've got here is the same as the view you have there. So that 25 meters per second at 60 degrees gets broken up into its x and y components. And the x component is the green arrow along the x-axis, and the y component is the value along the y-axis. Okay, so I've kind of run out of room on this diagram, but that's enough for right now from that diagram. Is everyone good so far? See, you could see how I've set that up. Okay, so I did initial position, I did final position. I'm almost halfway through done with the initial velocity, and I'll do the final velocity on the other whiteboard. Acceleration, you know what? Maybe I can add that to this diagram. Okay, so the acceleration, I'll draw it up here. There's an ax, but ax is 0, which is the whole point of putting the x-axis horizontally. Because the x-axis is horizontal and there's no gravitational pull to the left or the right, the x-axis measures how far to the left or how far to the right the motion is. And you know this ball is not being pulled to the left or pulled to the right because of gravity, so there's no x component. I won't even write it down. There is a y component, and acceleration due to gravity is down like that. Right, draw the direction over here. And so it's a negative because up is positive, and it's 9.8, but we will approximate it as 10 as we usually do, meters per second squared. Okay, so there's the acceleration. All right, so you know, initial position, final position, initial velocity, final velocity, acceleration, and time, and then you have all the pieces that you need from the diagram. All right, let me switch to back to this diagram here, or this whiteboard here, and now let me start solving the problem here. Okay, so move this down here, and just not to waste your time, I've got everything written here, but I won't go too fast. If I go too fast, I'm going to cut and paste here. But if I go too fast, just tell me and say, you know, you went too fast there. Okay, what do you have here? So the diagram, you just saw it, and reading off of the diagram, we got that the initial position, x naught, y naught, were both 0. Okay, we had that the final position was x was unknown, y was also unknown. And in fact, not only is the y unknown, but that's what we want to solve for. So I even said it here, solve for this. Okay, then the next thing, and this is where I started to run out of room, I had v naught x. So that's v naught is your initial velocity, x is the x component of the initial velocity, and that's obtained by calculating v naught cosine theta. And we had v naught y, which was v naught sine theta. Okay, and now you just plug in the numbers. Okay, so v naught x is cosine. V naught x is v naught cosine theta. That's 25. Is that what I said there? 25? Yeah, 25. Okay, I don't know. Okay, so 25 times cosine of 60 degrees. Cosine of 60 degrees is one of these easy to calculate cosines that you might have memorized. Cosine of 60 degrees is a half. Sine of 30 degrees is a half. Cosine of 60 degrees is a half. I don't know. It's just one of those numbers that if you've done enough sines and cosines, you memorize, and it's good to see these patterns. Okay, so half of 25 is 12.5 meters per second. Okay, this is the x component. So that green arrow that I drew in the horizontally, that's saying how fast is this ball moving just in the horizontal direction. Okay, and you might say, well, I can't picture that, like, because the ball is moving up and it's moving down. Just imagine that there's like the sun shining straight down on the ball and it's leaving a shadow, and you're just following the speed of the shadow as it moves along the ground. Okay, and so yeah, the ball goes up and down, but there's a shadow underneath it. There's a shadow underneath it, and if you were to follow how fast that shadow goes, that would be that green horizontal arrow. It travels at 12.5 meters per second. By the way, whatever that number is, it has to be less than 25, because when you break up the vector into its two components, both of the components have to be less than the total. Okay, so it's 12.5 in the x direction. In the y direction, 25 sine 60 degrees. That one you have to do on your calculator. Turns out to be 21.7. Okay, and that gives you the initial velocity. The final velocity, the x component, that's easy. Remember I said that there's no acceleration in the x direction. And so since there's no acceleration in the x direction, that v naught x, it doesn't speed up or slow down. Okay, and what that means is that if the x component of the velocity starts off at 12.5 meters per second, it continues at 12.5 meters per second. So I don't know if you can picture this, but if the ball's going up and it's coming down, it's following that arch. But if you just were to have like a shadow shining on the ground and you follow the velocity of the shadow along the ground, it would always travel at 12.5 meters per second. I'm assuming the sun is directly overhead, okay, which doesn't happen in our part of the world. But just try to picture that, the light shining straight down, and you just look at the shadow as the ball goes up and down. The shadow along the ground will always travel at 12.5 meters per second until it actually lands, okay? And so Vx, which is the final velocity, V naught x, which is the initial velocity, they stay the same. It stays the same all throughout the motion, 12.5 meters per second. If you were to try to catch this ball, if you're like a catcher and you're playing baseball and you're running underneath it, if you ran at 25 meters per second right underneath it, the ball would go up and it would come down and would land right in your hand. Okay, so there it is. Now the next one is a little harder to see, but I ask how long till it reaches maximum height, and you wonder what defines maximum height. Well, 1 minute it's going up, the next minute it's coming down. That's Vy measures the up and down, the motion up and down, the velocity up and down. Well, if it's going up one instant and then it stops and it comes down, at the moment it stops, Vy is 0. Okay. Now we had the same thing when 1D, when it went up and down, but now it's just the y component that is 0. And the reason is if you did the projection the other way, now this one's a little harder to picture in your mind. It's going up and down, but just picture like the y, like a projection in the y component. It would go up, the projection would go up and come down, and when it gets to the maximum height, Vy is 0. So whenever you see maximum height in these problems, that just basically translates into Vy being 0. Vx is not going to be 0 because Vx is going to be the constant. Vy will be 0. There's the acceleration. Ay is -10, and the time is what we want to calculate. Okay, so we did a lot of work to get those numbers, and I spent a lot of time, talking you through this. But if you can do this part of it, the rest of it tends to be easier. Most mistakes are made right at this point. Okay, so let me take a look here at questions in the live stream. I don't see any questions. Okay, so let me continue. Okay, and the next question is, what is the sorry, I didn't finish this one. How long till it reaches maximum height? And here what you want to do is you want to look at the 4 equations. Okay, and so this part tends to be a little easier, because once you have your values, you can take a look at these equations, go, well, which ones do I want to use? And I'm asking for time, so obviously it's not going to be number 3, okay, because number 3 doesn't have any time in it. All right. You could say, well, it reaches maximum height, okay, and if you take a look at number 4, it's all about vertical motion. It's not about motion up and down, so number 4 won't work. I mean, you could try to plug in the numbers, but you don't know x and you don't know t, so that's not going to work. It's number 2 actually will do it for you, so you've got Vy, which is the velocity at the very top, which is 0, Ay, which is the acceleration due to gravity, time you don't know, that's what you're solving for, and V naught, we just got that. Sorry. That's V naught y. I forgot the little subscript there. Okay, so v naught y. All right. All right, so use number 2. And again, I'm cutting and pasting, but I assume you guys are writing this in your notes. But hopefully I'm not going too fast. Again, just stop me if I go too fast. So using equation 2 to get to get t, I've rewritten equation 2 there. It's vy is equal to ay t plus v naught y. Okay, and so at the maximum height, vy is 0, ay is negative 10, t, and v naught y is 21.7. Just writing the numbers from above. Rearranging and solving it is really simple. I mean, it's just like bring the negative 10t to the other side. It's 10t is equal to 21.7. Divide both sides, and you get 2.71 seconds. Okay, so that answers part A. And looking in the chat here, no questions. Okay, all right, there's the first one. Now the next one is what maximum height is achieved. Okay, so what maximum height is achieved is basically you want to solve for the height, right? And you say, well, what is height in these things? So x is how far it travels horizontally, and y is how far it travels vertically. Y naught is where does it start? It starts at ground level. And y is like where does it end up? And that's the maximum height. So you want to use either equation 1 and substitute in time because you know time, or you could even use equation 3. Okay, so even though you don't have time there, you've got all the other pieces to it because you've got v naught y, you've got ay, you've got y is what you're trying to solve for. So you also know vy and v naught y, ay, y is what you're trying to solve for, and then there's y naught. I think I chose to use number 3. I did. Okay, but it's really up to you. It just kind of depends on like what you feel more comfortable with, and so. So I said use either 1 or 3. 1 would require you to substitute in the time. 3 would just requires you to substitute in the velocities. Okay, you might want to use both and then just see that you get the same answer. But I chose 3, and so let's go through it. Vy, that's the velocity at the top. It stops at the top, 0. Okay, v naught y, that was the y component initial velocity. That was 21.7, and that's squared. 2 times ay, which acceleration due to gravity is negative 10. Y minus y naught. Y naught was initial height was 0. So it's just y minus 0. And I mean, I don't know if I skipped too many steps here, but basically this is pretty easy to do. Maybe I could just write in the next step here. Okay. So well, I guess I got to get my calculator out here. I don't know. I don't want to skip too many steps, but so I had 21.7 squared like this, and so I get that 0 is equal to that, and then 2 times negative 10 times y is minus 20 20 times y, like that. Okay, and I think now it's pretty obvious what you do. Just bring the minus 20y to the other side, divide both sides by 20, and I got a maximum height of 23.5. All right, so that answers that question. All right. Everyone doing okay? Following along here? All right. So just quickly summarize what we've done. So, we had this situation where I'm throwing the ball up at 25 meters per second at 60 degrees. And how long until it reaches maximum height? And what is the maximum height? Okay. Now, the next one, I say how long before it lands on the top of the hill. You have to be really careful when I do this in a problem. I've changed something here. I've changed the final position. A and B were about the same final position, maximum height. Part B is about the other final position. And I actually started to make that mistake at the beginning. You remember where I was looking at the wrong final position. So at this point, when you realize that now I'm asking about a different final position. I'm not asking about when it reaches maximum height. I'm now asking about when it's starting to come down and it actually lands at the top of the hill. Revisit the diagram, okay? And so let's do that. Let's go back to the diagram here, okay? So here's the diagram again. And now we are not interested. Let me, I don't know, see if I can do this in purple here. Maybe if this will work. Now we're no longer asking about this red dot here. We're asking about, I don't know if that works any better. Right there, the final, that purple dot. I don't know if it comes, I can see it as purple. I don't know if it looks purple at your end, but you know, that final position right at the top of the hill. Okay, and you could see what changes. What changes are none of the initial values. So your initial position, x naught is 0, y naught is 0, they stay the same here like that. That's fine. Okay, it's the final positions which are wrong. Or I don't know if they've changed. Okay, so we have to rethink them. We have to rethink the final x and the final y. Okay, because they're different. All right, and so let's do that. So we go through all of them again: initial position, initial velocity, acceleration, and time. Okay, so we've convinced ourselves the initial position stays the same because nothing changed at you know, how I'm throwing it. Okay, it's all part of the same motion. I'm just looking at a different final point in the same motion. And so now we're at the top of the hill. We don't know how far we've traveled horizontally. That's one of the questions that I'm asking for. How far did we travel horizontally? But we do know why, because we've landed at the top of this hill. And if you read the question, I tell you that the hill is, let me reread it myself, it's 20, right? Yep, it's 20 meters high. So the final position, the y component, the height, is 20 meters. We don't know how far it traveled horizontally, but we do know that vertically it is 20 meters above the ground, okay, because it's at the top of that hill. All right, so there it is. The initial velocity, this piece here, that doesn't change, okay? The final velocity will, but we didn't know a lot about the final velocity anyhow. I'll do that on the other whiteboard. The acceleration didn't change. The time did. We're no longer looking at this time. We're going to be looking at a time there like that. So a typical mistake that's made is maybe you'll use the time from part A and B, or I get the time for part A, and you'll use that time for part B here, and that would be definitely wrong, because you know, one is the time to get the maximum height and the other is the time to get to the top of the hill. So go through all the steps. I mean, you might be able to reuse some of the values from before, but rethink the entire problem right from the beginning, because that change is you know, if you don't recognize the consequences of that change, then you're going to get the wrong values in there. Okay, let me get rid of that to not make this too messy. Okay, so there we go. Okay, let's go back to that other whiteboard. If you have any questions, you know, about what I just did there, well, I'll answer them in a second when I look at the other board here. All right, so over here, how long before it lands on the top of the hill? We go through all of the same steps as before, but now you're going to get these values. Okay, let me just cut and paste them. I'll go through them a step at a time so I'm not going too fast. The initial, let me highlight them. The initial position, that did not change, right? X naught and Y naught, they're still the same because I'm still throwing it from ground level. Okay, so there it is. The initial velocity, which I calculated in part A, that didn't change. Okay, it's the finals that changed. So let's revisit the final position. The final position, the x is unknown, but the y is now known. It's known to be 20 meters. Okay, take a look at what we had before. Before here we had that they were both unknown, like that. But now, because that was the maximum height, we didn't know the maximum height. Okay, but now we're in a different situation. We're in the situation where it landed, and we know how high above the ground it landed. It landed at 20 meters above the ground. Okay, so you can see how that changes. All right, and then finally, the final velocity. Well, the x part of it doesn't change for the same reason as before. The v naught x and vx, I mean, the velocity in the x direction is just a constant. There's no acceleration in x, so that remains the same. Vy, we don't know. We don't know. Before we said here, let me just go back to that and highlight it. When we were at maximum height, we said, oh, maximum height, that means that Vy is 0, right, at maximum height. But now we're on the way down. This ball is coming down, and so Vy is not 0 anymore. All right, it's got some negative value because it's coming down. All right, so you could see that if you just blindly reuse the same values above, you would get the wrong answer. What changed? What changed was the final. So so you have to rethink the final values carefully. Okay. And then, of course, AY doesn't change because it's constant all the way through the problem. It was unknown before. It's unknown now, but it's a different unknown. Okay, so don't put in, like before we found that the value was, until it reached maximum height, we found that it was 2.17 seconds. But that's the time to get the maximum height. That's not the time to get to the top of the hill. It's going to be longer to get to the top of the hill. So, like if you just blindly start to put in values that you found here and there, you'll mess it up. Okay, you don't know how long you now know how long it takes to get the maximum height, but you don't know how long it takes to get to the top of the hill. Okay, and so that one is a question mark. Okay, and so now how long does it take to get to the top of the hill? Well, you take a look at those equations again, and you realize that you have to use equation number 1. Okay, so again, I'm going to cut and paste very quickly here. You're going to see it appear very quickly, but let me explain. Maybe I should just go back quickly to those 4 equations. All right, I'm asking how long. How long is time? You could take a look and you see that there's time in number 4, time in number 2, and time in number 1. Number 4, you can't use it because you don't know x and you don't know t. Okay. Number 2, you can't use. That's what we used it before, but we can't use it now because you don't know Vy. You don't know time and you don't know Vy. You have to go to equation number 1. Equation number 1 is the one that'll give it to you, okay? So, and then equation number 3 can't be it either because it's got no time in it, okay? So it's just by this process of elimination, you think, well, what can I plug in to get it? And you want, one equation with one unknown in it, time. And so if there's no time in it, it's not going to work at all. And the other ones don't work. The 2 with time don't work because you don't know one of the other variables. So equation number 1 is the only one that's going to work. And so if we go down here, sorry, I'm jumping around a lot, but I wanted to show you like how I reasoned that out. Okay, so if you take a look there, I say use equation number 1 to find the time. All right, you substitute in the values that we just got, that we just read off of the diagram, and y was 20. And that's the height, is the top of the hill. 1/2 ay, it's -10. T squared we don't know. And then there's v naught y, we found that to be 21.7 times t, plus y naught, that was 0. That was started off at ground level. Okay, so there's, just like plugging the numbers in. And now it's a matter of simplifying it. So what I did was I guess the first step, a half times -10 is -5 here. Okay, and then there was the 21.7, and then that 20 on the right hand side, I subtracted 20 from both sides, so I get -20 on that side. The reason I did it was to get it into this form, and the reason I got it into that form was because it's quadratic. Okay, so once you're at the quadratic, you know what to do, hopefully at this point, is solve the quadratic equation. I'm going to show you a little secret, okay, on how to quickly solve quadratics. I'm going to do it the long way first. I personally, at this point, I don't like capital A in the quadratic equation. I like dividing out by capital A in the quadratic equation itself, and then it solves a little bit faster. So you can see here that I have -5t squared, so I divided everything by -5. -5 divided by -5 is 1. 21.7 divided by -5 is -4.34. And then -20 divided by -5 is +4. Okay, and then I take a look at this and I go, all right, there's a quadratic, and a is 1 because I made it 1. By dividing by that -5, I made a 1. Okay, b is -4.34. Okay, and c is 4. All right, and the quadratic equation is t is equal to minus b plus or minus, there's two roots, one for the plus and one for the minus, so plus and minus square root of b squared minus 4ac divided by 2a. Probably memorize this in, I don't know, grade 11 or something like that. Okay, and a is 1, and then just plug in all the other values, and I get those 2 values there like that. So a little secret here. I don't know if it's a secret, I've told some people, but you might as well know about this site. There's a lot of sites online where you could just plug in the numbers and it'll solve the quadratic for you. It's just a web page, and this web page, like a lot of calculators will do this for you. It's just a web page, and you just plug into the A, B, and C into the web page, and it'll solve it. So math.com has a lot of like these like very simple web pages where it'll solve equations for you. Okay, and math.com student calculator source quadratic. I mean, that's kind of a mouthful to remember there. You could just Google for solve quadratic equation online. Solve quadratic equation online. There's dozens of these sites, you know, and so uh, there it is. Or a lot of programmable calculators have that, and you know, feel free to use them because this is an open book test and you can go ahead and use that. But you know, if you crunch this through, you're going to get two times. And one time is 3.01 seconds and the other one's 1.33 seconds. And you say to yourself, whoops, you say to yourself, well, which one do I want? Do I want the 3.01 or the 1.33? So I'm going to interpret that for you, okay? And to do that, let me go back to the diagram. Let me just see if there's any questions in the chat before I do. Geez, guys are quiet. You know, don't be afraid to ask questions. And all right, let me switch over to the other whiteboard there, and let me interpret. So what we're doing is I'm trying to explain to you what that 3 seconds is, the 1.33 seconds, the 3.01 seconds, the 1.33 seconds. I'm also going to show you how they relate to the 2.17 seconds. Okay, so let me switch. And let me draw a few things here. So we know at this point, I'm running out of colors to use. I think I'll continue to use purple. We know that at this point here, the maximum height, that occurs at, it's not a question mark anymore, that occurs at 2.17 seconds. Okay? Now, 0 seconds is down here at the origin. And let me draw that last line in there. Now I'm making a mess of my diagram. The 25 meter height, okay? And sorry, the 20 meter height. We know that it's going to start at 0 seconds and it's going to pass the 25 meter height, the 20 meter height. I keep saying 25, the 25 meter height right there. That's one time at which it passes the 25 meter height. And then it's over here at maximum height at 2.17 seconds, and then it reaches this point at a later time. I think it's pretty obvious that the earlier time is going to be the 1.33 seconds. So it gets to this point right here at 1.33 seconds on the way up. It passes 20 meters, the 20 meter height on the way up after 1.33 seconds. It reaches maximum height at 2.17 seconds, and it reaches the top of the hill at 3.01 seconds. Okay, that looks awful. I don't know if I can draw that a little better. 1 second. Okay. I'm sorry, guys. There we go. All right, you got it. Okay. So it's pretty obvious that we want the 3 second. Okay, 3.01. All right. Now here's what's interesting about this problem. The interesting thing is that the 2.17 second, remember the parabola is totally symmetrical? It's right in the middle. The 2.17 seconds is right in the middle of the 1.33 seconds and the 3.01 seconds, okay? So it's kind of like the maximum height is in the middle. Like if you were to measure the time it takes to go, and we'll do that in just a second, the time it takes to go from 1.33 seconds to maximum height, and then you measure the time it takes to go from the maximum height to the, again, to the 20 meter height here, but on the top of the hill, it turns out that those two parts of the parabola are exactly the same amount of time, okay? Which makes sense because the parabola is symmetrical about the maximum height here. And now I've made a total mess of the diagram, but that's okay. We're done with it, okay? So let's switch back here to this. And so there's another thing. This isn't part of the problem. The answer we want is going to be the 3.10 seconds. But let me just show you something else I did. Okay. So here's the final part of it. Just copy and pasting in here like that. So I say here, see the diagram for why you want 3.01 seconds. We just did that because it's not the time. So we're passing that 20 meter mark twice, once on the way up, once on the way down. But the ball lands on the top of the hill on the way down, so we want the longer time, the 3.01 seconds. Don't do this thing like where you say, oh, it's I just want the positive time. That happens if you're on the top of a hill and you fire down. But if you're on the bottom of the hill and you fire up, you're going to get two positive times. You go, which one do you want? Well, it depends. In this case, you want the longer one because you're hitting it on the way down. Sometimes you might hit a target on the way up, okay? And I don't try to be tricky in any of my problems, but just, think about it. On the way up, is different than on the way down. You're going to pass the 20-meter mark twice, the 20-meter height twice, once on the way up and once on the way down. Think about which one you want, and that'll determine the time, okay? So, by the way, the maximum height was obtained at 2.17 seconds, and notice that the 3.01 seconds, that's like you take the 2.17 and you add 0.84. So if you take 2.7 and add 0.84, that's the time it takes to go from the maximum height to the top of the hill, okay? Conversely, take a look at this. If you had 2.71 and you subtract 0.08, then that's the time it takes to go from that 20-meter mark to the maximum height. In other words, that 0.84 seconds, which I just obtained by subtracting, 3.01, 2.17 from 3.01, that 0.084 seconds, let me go back to the whiteboard, that is exactly this time where I've, tried to etch it in here in purple, the time that it takes to go from there to there, and the time it takes to go from there to there. Yeah, this diagram is a total mess. We're done with it. Okay, so I think I made it clear. It's a little hard for me to draw it, but I think you got the idea. All right, let me look in the chat here. We're almost done with this problem, and so well, there it is. Okay, once you get that time, the next two are pretty easy to do. All right. Okay, so question was how long until it lands? 3.01 seconds. Next question. Always make sure you've answered the question, because you get lost doing all the steps and you go, did I really answer the question? And yeah, okay. All right. How far did it travel horizontally? So horizontally is along x. So we go back to the equations and scroll back here to these equations. Let me highlight them so you can see them in the middle of all my other text. There are those four equations that describe 2D motion. Constant A, okay, and we want to find how far did it travel horizontally, and so that's x, and there's only one equation with x. It's number 4. You have to use number 4, okay, but now you know the time, and so you can use number 4. All right, so like I said, the next two are very easy. The time was a hard one because you required the quadratic, and not only do you require the quadratic, you need to interpret the quadratic. Okay, so how far did it travel horizontally? All right, cutting and pasting here. All right. So substitute into equation 4 to find x. There's equation 4. X is equal to v naught x t plus x naught. All right. And v naught x, just look above, that was the 12.5. The t is how long until it lands, and that's going to be 3.01 seconds. We found that, okay? And it started at 0 on our ruler horizontally. That x naught was 0, and so that gives you 37.6 meters, okay? So that's how far it traveled horizontally before it landed. Okay, so yeah, question D was pretty straightforward. And finally, question E is what is the velocity just before it hits the top of the hill? And answer with just the magnitude, okay? So I've explained this idea of just before. And here I actually wrote it in explicitly to really emphasize it in your minds what's going on here. Those equations, those four equations that I highlighted, they know nothing about the ground or the top of hills or anything like that. All they know is an infinite parabola, okay? And so you might say in your mind, you might say, well, after it hits the hill, it might bounce a few times, but eventually it'll stop. So the final velocity is 0. End of story. Well, no. I mean, yes, that is physically true, but that's not going to come out of those equations, okay? And you shouldn't substitute those values into those equations because, like I said, they don't know anything about the acceleration due to the collision with the ground. All those equations know about is the acceleration due to gravity. As soon as the ball starts to hit the ground, like if just before it hits the ground, it's just gravity. But as soon as it starts to hit the ground, there's gravity and the ground, and those equations no longer apply, okay? And in fact, like, I mean, just think about how complicated the bouncing motion is, okay? So it's not like it hits the ground and stops. It's going to bounce. That's because there's a whole complicated new set of like interactions that are going on once the ball encounters the ground. So if I were to say something like, "What is the velocity after the ball hits the ground?" Well, then you could justifiably say, "There's no way I can answer that because you have none of the details of how the interaction between the ball and the ground are." I mean, does it just hit and stop? Does it hit and bounce twice? Does it bounce 20 times? Like, what's the nature of all that interaction? None of that information is in those equations, okay? So it's the velocity just before it hits the ground, and that's not zero, okay? I think that's pretty intuitively obvious. Even if I were to say, what's the velocity at the top of the hill or when it hits the top of the hill, you really should ask the question. You should change it in your mind just before it hits and then solve that way. Okay, so it's worth repeating because I mean, physics is not just it's not just math. We use a lot of mathematical equations and so on, but those mathematical equations don't live in some kind of like in math, like a lot of math problems are solved for the following, and there's no context at all. Here, all of these mathematical equations are in the context of some kind of experimental real world situation, and so they require that interpretation, that physical interpretation, okay? And so that's why I'm going through this very carefully, okay? There are a lot of people that are good at math and they have difficulties in physics precisely because they have difficulties with that interpretation, okay? So all right, well, you look at the four equations and go, well, what am I trying to solve for? Well, you're trying to solve for the final velocity and the magnitude. Now magnitude, I say magnitude here, but magnitude, that's a polar thing, okay? In the lecture, the pre-recorded lecture on vectors, that was my R, okay? Now that was abstract math because I just had to teach you how to work with vectors. But that R, that magnitude, it depends on what kind of a vector it is. If it's a position vector, then it really is an R, it's just a distance. But if it's a velocity vector, it's how fast you're going, irrespective of your direction. That's known as the magnitude, okay? So I asked for the magnitude, and that's polar, but nothing in the problem right now up to this point was polar. It's all Cartesian. So you ask yourself, how do I get a magnitude out of x and y values? And you need both Vx and Vy to do that. Okay, you'll need both. All right, now Vx we already have. Okay, so what we have to do is calculate Vy. Well, let me show you that. Again, I'm cutting and pasting. Mostly I find that I make less errors when I do this, but whoa, that's not what I wanted. But I don't want to go too fast, so I am depending on you guys to yell at me if I go too fast here, okay? All right, oh, let me move that down just a little bit. Okay, good. Okay, so to get the magnitude, we want both Vx and Vy. Okay, now it's not V naught x and V naught y because that's the initial. That's like where I throw it. We want it just before it hits the ground. Okay, so that's Vx and Vy. All right. Now we know that Vx is the same as V naught x. Because why? Because there's no acceleration horizontally. Like you don't release a ball, it moves straight down. It moves straight along the y-axis. You don't release something and it falls a little bit to the left or a little bit to the right. That would be weird, okay? It falls straight down. So there's no x component to the acceleration. So acceleration means change in velocity. So if there's no change in velocity in the x direction, the Vx stays the same. So if it started off with a V naught x of 12.5, it ends with a Vx of 12.5. So we've got the Vx part. We've got the x component of velocity. We need the y component, and you can look through those equations, and it turns out once again that you could use either equation 1 or you could use you could use equation 2 or you could use equation 3. And I chose equation 3 again. I'm not sure why, because you could use both of them. I just chose that one. But here it is. So it's Vy squared. That's the y component. That's what we're trying to solve for. Okay, squared is equal to V naught y squared plus 2ay y minus y naught. Okay, so there it is. That's equation number 3. All right, and so Vy squared, all right, is the V naught y was 21.7 squared plus 2 times ay is negative 10 y was 20, that's the top of the hill, minus y naught is 0. So I didn't write that in here, but maybe, I don't know, just write it in here, minus 0. Okay, now it's pretty obvious how what the substitutions are. Y was 20, y naught was 0. Okay, and now we get that, solving this on your calculator, you get that Vy squared is 70.89. I guess I should round that off because we're doing 3 significant figures. So it's 70.9 like that. Okay, but that's Vy squared. When you take the square root, you get both positive and negative solutions. So don't forget that. Okay, so if you get that Vy squared is 70.9, that actually means that Vy is either positive or negative 8.49. Now, why am I emphasizing that? So this is the quick aside. I'll just maybe do it down here. If you have like just pick another variable like z squared like that is equal to 4, and I say solve for z. What's z equal to? Well, most people will say, oh, z is equal to 2. Yeah, that's one possibility. Here's the other possibility. The other possibility is negative 2. Okay, even that simple equation z squared is equal to 4 is a quadratic, and there are two solutions. There's the positive and the negative. Why? Because 2 times 2 is 4, but negative 2 times negative 2 is also 4. Okay, and the reason that's important in this situation is because on the way down, because you're hitting it on the way down, Vy is negative. And so, yeah, there's a positive solution and a negative solution, but you choose the negative solution because it's on the way down. Okay, it won't make a difference for the magnitude, but it would make a difference for the direction. Okay, it would make a difference if I asked you the direction, because on the way up, Vy is positive, and you'd have an angle which is a positive angle, but on the way down, you'd actually have a negative. You'd have an angle on the way up. You have an angle in the first quadrant. On the way down, you actually have an angle in the fourth quadrant. Okay, and so I didn't ask for the angle in this problem, but I just wanted to emphasize that. And so if you didn't, for instance, you forget, you go, well, if a v square, you just do this on your calculator. Just take 70.9 and take the square root. Calculator is not going to give you the negative solution. It just gives you 8.42. And if you forget that there's a negative solution, you might just use the positive solution blindly, and then you get the wrong direction. Okay, so just keep that in mind. Whenever you got something squared is equal to a number, a positive number, there are two solutions, the positive and the negative. Okay, and so there it is on the way down. Now, at this point, we still didn't answer the question. At this point, we have Vx and Vy. Okay, so let me just write that in here. All right. So Vx is 12.5 meters per second and Vy is negative 8.42, but we need the magnitude, and that's the polar equivalent of r. Okay, now how do you get a magnitude from an x and a y component? It's the Pythagorean theorem. Okay, and so the magnitude just means how fast are you going, irrespective of the direction. I don't care which way you're going. What just happened there? Oh, I cut and paste too much. Hold on. 1 second here. Copy, paste. There we go. Okay. So magnitude just means how fast, irrespective of the direction. Okay. And so so v is equal to the square root of vx squared plus vy squared. So that's 12.5 squared plus negative 8.4, but the negative gets squared with it. Okay. So it's negative 8.4 all squared, and then you take the square root of that, and I got 15.1 meters per second. Okay, so that's how fast it hits the ground. All right, so we're a little over the 1 hour mark. The next question will be very fast. Okay, but we've answered that question. I went through it very slowly. Normally, if you get good at these things, you could probably answer it in a quarter of the time, like 15 minutes maximum. Okay, but I wanted to make sure that you understood every single step. Okay, so how I reasoned it through. All right, and so there it is. There's question number 1. Let me see if there's any questions in the chat here. Nothing that I can see. Okay, so here's what you do on your own. First of all, just repeat the problem I did. Just repeat it. Okay, you could use the same numbers. You can even try different numbers, but be careful. If you use a number like if you decrease that 25 meters per second, it might not hit the top of the hill. Okay, in which case you'll get a negative square root when you go to solve the quadratic equation. So it might be worth doing it just to see that you get that. But that's what might happen. Okay, but you know what? Even if you repeat it with the same numbers, there's still a lot of steps. Okay. Then repeat the problem again, but this time repeat it and assume there's no hill. So basically, I launch the ball from ground level, it goes up and it comes down and it also lands at ground level. Okay, so it starts at ground level and it ends up at ground level. And then repeat it again. Do all of the same 5 questions again, parts A through E. But this time, assume that you're standing on top of the 20-meter hill and it lands at ground level. Okay, which is the opposite, right? For that one, there's no danger. There's no danger that you won't throw it fast enough because you're not trying to get up on top of the hill. Okay, but there it is. So you could, in part 3, you could safely change the values of the numbers and just see what happens. Okay, so do those on your own as practice. With questions 1, 2, and 3, all 3 of them, you pretty much have all the possibilities, for 2D constant A. All right. I'm going to just do number 4. It's really easy. All the circular motion stuff is I don't know. I mean, I shouldn't say whether it's easy, it's whether you guys find it easy or not. But I mean, my experience is that uniform circular motion stuff is really straightforward. Okay, and so here's the problem I have. Okay, I'm riding a bicycle around a corner. Okay, a corner is kind of a circle, even if it's not a full circle. It's like, say, a quarter of a circle, and the corner has a radius of 7 meters. Okay, it's like 20 feet, which sounds about 21 feet. Sounds about right for the radius of a corner. Okay, so I'm riding a bicycle around a corner of radius 7 meters. The fastest I can go without slipping. Okay, and don't want to kill myself on the bike. Okay, so I don't want to slip. Is about a quarter of the acceleration due to gravity. All right, so there's an acceleration due to gravity. At a quarter of that, if I'm under a quarter of that, I'm fine. If I'm over a quarter of the acceleration due to gravity, then I'm in danger of slipping. And so how fast can I go around the corner? How fast can I go around the turn safely? Okay, so basically whenever you see the words how fast, that's velocity. Okay, and everything in uniform circular motion is just magnitude. I mean, there is a direction, the relative directions, like you saw in the pre-recorded video. There's the radial vector. The position is from the center of the circle to the point on the circle. The acceleration is from the point on the circle back towards the middle. That's why it's called centripetal, center seeking, centripetal. Petere is Latin for seek. Okay, so it's the center seeking. Acceleration is in towards the center, and the velocity is tangential. It's along the outside of the circle. Okay, and so, well, let's solve it. All right, and so where do I have it here? Let me just grab the entire solution. All right, paste. All right, and scroll down too far. All right, so what do we have here? The 3 kinematic quantities are r for the radius. Okay, that's like your position, but it's not exactly position because position is where you are, but it's the magnitude of the position, and that never changes. That's the radius. So that's 7 meters. I gave you that. The acceleration, I said the best you could do is a quarter of the acceleration due to gravity. Okay, 1/4 g. All right. So a quarter is 0.25, and g is 10 meters per second squared. So the fastest I can go around this corner I can't go faster than an acceleration of 2.5 meters per second squared. Otherwise, I'm in danger of slipping. Okay, so there's 1/4 g. All right, and the 3 equations that you need to know. So these are not the directions; these are just the magnitudes. But that's good enough for this problem. Is the velocity is related to the radius and the period, which is the time it takes to go around one circle. That's capital T. V is equal to 2 pi r over capital T. Okay, so again, T is the period. Period just means the time for one cycle. So one lap around the circle. Now, I'm not even making a full lap because I'm just going around the corner. Okay, so I didn't even ask about the period, but there it is. Okay, so velocity is related to r and t through equation 1. The acceleration is related to r and t by equation 2. And then finally, the acceleration, velocity, and radius are related to one another with equation 3. Okay? And I don't give you any information about time in this problem or period in this problem. So it's pretty obvious that you use equation number 3. And so and we're solving for v squared, though, so you have to rearrange it. Okay, so don't think that, like just because these equations have like v and a on the one side, you might have to rearrange them. Okay, so you pick them based on what's the unknown, one unknown. You want one equation with one unknown, but you might have to isolate that unknown. I think it's pretty obvious, but it bears repeating. Isolate that unknown. So you have v squared is equal to ar. That's just equation number 3, where what do I do? I multiply both sides by r, and then I take the square root, and I get that v is equal to the square root of ar. Okay, and a was 2.5 meters per second squared, and r is 7, and it just turns out to be 4.18 meters per second. Okay, so that's the fastest I could be traveling. That's the fastest velocity I could be doing going around the corner there. Okay, and I just converted that to I didn't ask for that, but I converted it to kilometers per hour and then miles per hour, just to give you an idea. I tried to pick some realistic numbers here, and if you're going 15 kilometers per hour, about 10 miles an hour, that sounds about right. You're going around a corner on a bike, 10 miles an hour. I might be able to do a little bit more than that, but I don't know. I'm a bit chicken. I don't want to risk myself. So 10 miles an hour sounds about right. Okay, for like the fastest you'd go around a corner on a bike. All right, these problems are really simple. I don't think I can make them too much more complicated than this and what you've seen. And so I'm not going to belabor it, but there it is. That's the end of the I don't know if you call this a lecture or tutorial, whatever. But if there's any questions, I'll just wait a little bit longer. But other than that, we're done. Okay, and there it is. Okay, so let me just type in the chat here. Does anyone have any questions? Else we're done. And if you can't think of something right now and you do later, feel free to jump in on the Google Hangout in the evenings. So people do, even for just a minute, there's people that'll pop in and they'll say, I didn't quite understand this thing, and it just like literally takes me a minute to explain it, and that's fine too. Is everyone good? So I always get a little nervous when there's no response, because I feel that maybe everyone has fallen asleep at the keyboard. Can I end the stream? Oh, I'm not getting any feedback, so I don't know here. All right, guys, I'm just going to go ahead and end the stream if I don't see any other questions. So, all right, bye-bye then. I'm ending the stream. I see people are popping out, but I'm not getting any confirmation in the chat. All right, see ya.